Hey there. All right, so today we're doing kind of an introduction to matrices, which is plural for matrix, and it's just ultimately a matrix is just an array of numbers, and we're just going to do some basic operations on them today. As we introduce this idea of matrices, just some basic terminology that you need to be familiar with as we talk about them. Already talked about how it's an array of numbers, just a way to organize information. And so you can see here, a matrix is going to have like this bracket here, and then you're going to have different elements within inside this matrix. This might be a better example of what you're going to be seeing. Notice there's no commas between the numbers. You just have to be organized or neat enough to leave spaces so you can distinguish one element from the next. It does have a dimension to it. It's always going to be rectangular, but we describe its dimension by how many rows there are and how many columns there are. So like it's an M by N matrix. So rows by columns. How many rows downward, how many columns across. Now, when you have a particular entry inside of this matrix, it's notated by its row and column placement. And so if you think of like this, it's I row, J column. And so you'll have some value in here with a sub number that tells you which position it is in the matrix. So you can see like this one right here. This is in your second row in your third column, so it has a sub number of 23. This one right here, it is in the third row, first column, it has a sub number of 31. So let's just take this example that I have right here. Could you tell me what the dimensions of it? Could you tell me what the specific entry would be they're asking for? So go ahead and see if you could do that off the top of your head. Hopefully you could recognize that there are 2 rows and 4 columns. So this is a 2 by 4 matrix. And when you look at this sub number as a 23, that's the second row, third column would be a 1. That would be the element they're looking for. We name matrices with a capital letter, so then we can start talking about them in reference to just what we'll call it matrix A. Instead of having to write out the entire matrix, we will just name them with capital letters. Now, if you're going to have what we call equivalent matrices, then they pretty much have to be identical. Not only will they need to have the same dimensions, but they also have to have all the same corresponding elements. So when you look at this example, this is a 3 by 2 matrix. This also is a 3 by 2 matrix. Notice that this together is an element right here. This is its own element, and they just have plenty of space in here to distinguish one from the next. No commas. So now what they want us to do in this example is to solve for the different values within that matrix. So when I look at this W minus 2, this is first row, first column. It needs to be identical to this. So that means W minus 2 is going to have to be equal to 8. So to solve for W just means, all right, so W is going to have to be a 10, just adding 2 to both sides there. The next one would be this element. I see that it's a negative 2x. It corresponds to this negative 4. So that means that our negative 2x is going to have to be the same as a negative 4, divide by negative 2, and we can see what x is equal to. Now, you take a moment, go see if you can figure out the y and the z. So you should have gotten y to be 9. That was an easy one. And then you'd have to do a little algebra on the next one. 4z minus 10 has to be equivalent to negative 2. So I'm going to add the 10, divide by the 4. So z is 2, y is 9. So those were just kind of some terminology and some basic information about matrices. Now let's start those operations. If we're going to add and subtract two matrices, they have to be the same dimensions. It's the only way that this will work. And then once you determine, yep, in this case, I have a 3 by 2 and another 3 by 2. So they're able to be added or subtracted. And all you have to do is add or subtract the corresponding elements. All right, so to do this particular problem, it's a 3 by 2, and when I add the two together, I'm going to end up with another 3 by 2 matrix. To find this first row, first column, all we're going to do is take the first row, first column elements, and we're going to add them together. So I end up with a 4 plus 2. For this position, I'm going to have a -3 plus -1. So let's start filling in. The 4 plus 2 is a 6. A -3 plus a -1 is a -4. The biggest issue here is getting your negatives mixed up here. So especially if this ends up being like a minus sign. If that's a minus sign, now you're really having to pay attention because you'll have a negative minus a negative kind of thing. All right, here we go. 0 plus 1 is going to get us a 1. 7 plus a -7, well, that's just a 0. We have a 2 plus a 3, that's a 5. And a -1 plus a 5, that's a 4. All right, so nothing crazy there, just adding corresponding parts of the matrix. Now, when we do scalar multiplication, this is just when you take a particular matrix and you scale it, either making all the numbers larger or smaller, but all by the same scale. And so an example here, I've given you a matrix A. It's a 3 by 2 matrix, and we are scaling it by 3. So the size is going to be the same here. It's still going to be a 3 by 2, but we're going to take each element in the matrix and multiply it by 3. So the 4 right here gets multiplied by 3. And so now this is a 12. And the -3 times a 3 is a -9. And the 0 times the 3 is still 0. 7 times 3, 2 times 3, -1 times 3. So not real difficult there. You're just multiplying them all by the same value. Now, can we maybe tie this all together into doing many operations at once? Sure we can. All right, so here I go. I've got these two matrices, went ahead and called them A and B again. They're both 3 by 3s, so they're fair game to add and subtract. And actually what I want to do is I want to do the scalar multiplication on the A, and then I want to subtract the B. So here's how this is going to play out. I'm going to write really big here. You might want to wait and see how we do this, and then maybe pause the video and add in the notes. Let's just watch for just a second. So I want to do 2 times the value in A, and then I want to subtract the B. So for this first spot, first row, first column, I'm going to take 2 times the A element, which would be a 2, and then I'm going to subtract that same element, a lot of 2's here, but I'm looking at this number and this number. Okay, let's do it again. First row, second column, I'd take a 2 times the A element, and then subtract the B element. And then I would do it again, 2 times the A, subtract the B. So now ideally for matrices to be especially beneficial, it's nice to be able to do some mental math in here, so I'm not writing this all out. I don't necessarily save a whole lot of time if I'm going to write it all out. So the question is, could you in your head take 2 times 2, say that's 4, and then subtract 2? Do I have to write this out to be able to do that? And so I'm hoping you're saying, I think I can maybe do that in my head. So with that being said, I'm going to try to do the rest of them in my head, which means I'm going to erase this stuff off of here, and I'm going to do it in my head now. And now is when maybe you start writing. It doesn't have to be near as big of a matrix if we're going to be able to do this stuff in our head. So I'm going to kind of shrink this down. And here I go. So it's 2 times A minus B. So 2 times 2 is 4, minus 2 is 2. Do it again. 2 times 2 is 4, minus 0. That's just a 4. 2 times 4 is 8 minus 0. And we keep on going. 2 times negative 3, that's a negative 6. Minus 1 is a negative 7. 2 times 0 is 0. 0 minus negative 4 is a plus 4. 2 times negative 1, that's a negative 2 minus a 3. A negative 2 minus a 3. This is what I'm saying, like, you got to be careful with those negatives. We should end up with a negative 5 on that. All right, you do the last row on your own. All right, hopefully you got a 5 and a negative 1 and a 2. All right, so I think we're going to kind of move on from adding and subtracting and scalar multiplication, and let's jump into something that is really going to be the trickiest thing of all the stuff we're doing today. And I say it's tricky just because it's different and maybe not what you would have thought you were doing, but it's kind of fun, actually. So to do matrix multiplication, if you're going to multiply two matrices together, what you do not do is just grab their corresponding parts and multiply them like we did with addition and subtraction. That's actually not how you multiply two matrices together. And in fact, not all matrices can be multiplied. The only way you can multiply them is the number of columns in the first matrix matches the number of rows in the second. Okay, so let's look at what that would be like. So here's matrix A, some m by n matrix. B would have to have the same number of rows that A did columns. So these two numbers here, when you set them next to each other, these two values have to be the same. If they're the same, then your resulting matrix after you multiply them will be the outer numbers here. It'll be an M by P matrix. And the reason that it plays out like this is because you do not multiply matrices that are just their corresponding elements. In fact, sometimes matrices that are the same dimensions cannot be multiplied. All right, let's take a look at an example here. I have given you two matrices, A and B. Notice that the dimensions are a 3 by 2, so 3 by 2, and this one is a 2 by 3. So the first question, can they be multiplied? Well, you check the columns and the rows. Yep, they match, so they can be multiplied. And the resulting matrix would be a 3 by 3. All right, so now let's talk about how do we actually multiply them. It is not like adding, subtracting, where you match up the corresponding elements. It's actually different than that, especially when you consider that your result is a different shape. So looking at this, I've kind of drawn a 3 by 3 here. It's a little bit weird, looks a little rectangularish, but it's going to end up a square matrix, 3 rows, 3 columns. And to find the value to put in the first row, first column, what you actually do is you take your first row times your first column, and you take this first element times this first element, and you take the second element times the second, and you add them together, and that's what goes in this spot. Now, again, this takes a little bit of mental math if you're going to do that just all in your head. Otherwise, you might have like an intermediate matrix. You set it up, it's really big, and you place this computation right here. You could put that right here and then kind of come back and do it. As you do it initially, it's harder to keep track in your head everything you're doing, but we get better at it. Okay, so then you can see that I would end up with a 5 and a 24. So this is going to equal 29, and that goes in the first slot here. First row, first column. Then I'm going to take the first row times the second column. So you can see here, first row, second column. I'm going to take the -1 times the 5. That's what I wrote here. And the 6 times the -1, wrote that here. And I'm going to add those together. So that's a -5 and a -6. Added together is a -11. I don't know why I wrote a 10. -11. Okay. Let's try again. First row, third column. So -1 times 3. I'm going to at least just do that in my head. -1 times 3 plus, then I have a 6 times a 4. So that's going to be a 21 that goes there. And now you've done all the operations with the first row and you're ready to move on to the second row. So to get the second row, you're going to take the second row, first column. So that's a -20 and a 0. Well, that's easy. That's just -20. So let's keep going. I've done drawn kind of the picture out. Let's just see if we can look up here at the original ones. Okay, so we are ready for the second row, second column. So here we go. Second row, second column. That's a 4 times a 5. That's 20 and 0. That's 20. Second row. Whoa, that's going to mess everything up. Okay, right there. All right. Second row, third column. So 4 times 3 is 12 and 0. Now, this can get harder if you get bigger matrices, you're having to keep track of 3 or 4 numbers. I'm really only having to keep track of 2 numbers, so I feel like that's pretty doable to do in our head. So now I'm on to my third row, first column, -2 and -5. That's 10 and -20. 10 and -20 is a -10. Now, I hope I don't make an error here. So bear with me. You might just have to tell me tomorrow if you see I goofed it up. But next one is a -2 times a 5. So just to show -2 and a 5, that's a -10 and a +5. -5. All right. And then last one, -2 and 3. So that's -6 and -20. That's a -26. And there we go. That's multiplying. So that's definitely the trickier version than all the other stuff, but it's kind of fun once you get in your groove. So let's look at some other ones here. I have one here for you to do on your own. Since it's a video, I'm going to go ahead and go through it one more time. Or what you could do here is you could pause the video and go try it on your own and then come back. And if you need to fast forward a little bit, that'd be great. But I'll go ahead and go through this one in case you're iffy. All right, so first thing you always have to do is decide if it's even possible to multiply. I have a 3 by 2 and a 2 by 2. So yes, it can be done. My result is another 3 by 2. So I'm going to be taking first row, first column. So I'm going to get rid of that so it doesn't mess me up totally, but here we go. So I've got a 12 and 5, 17. I've got a 0 and 10. I've got, now I'm moving to second row, 18 and 3. Then I've got 0 and 6. Going to the third row, first column. So that's a 6 and a -3. The last one is a 0 and a -6. And there we go. Okay, let's go and look at what happens when you try to take a matrix and you try to square it. Okay, so first thought might be, hey, I'm just going to square each element in the matrix. Nope. Squaring is ultimately the same as multiplying. So if I wanted to find A squared, what I would have to do is write out the A matrix twice and go through this process of multiplying. Now, so in this case, though, you still have to consider that you're going to have 2 matrices like this. And so this is a 2 by 3, and I'm going to multiply it by another 2 by 3 itself. So if you notice, oh, wait a second, these are not going to be able to multiply. So in this case, you cannot even square it. So in the same way you can't multiply all matrices, they cannot all necessarily be squared either. And we would write not possible for this. All right. Now the next thing I have here is looking at when you are multiplying matrices together? Are they commutative? Commutative, remember from back in Algebra 1, means that when you multiply two numbers together, it doesn't matter the order that you multiply them, you still get the same thing. So yeah, multiplication is commutative. Addition is commutative. Subtraction and division are not. So then the question is, can you multiply matrices? Is that commutative? So in other words, is A times B the same as a B times A? Now, if you think about this for a second, first of all, the only way you could even consider this possibility is if these, now think about it, in this version, the rows, well, really it's the columns of A have to match the rows of B. And over here, it's the other way around. So the only way this could ever work is if your matrices were what we call a square matrix, where it's a 2 by 2. So your rows and columns are the same, so it would work both ways. So I've given us a couple square matrices, and we're going to check it real quick and see if A times B. So let's do this real quick. Let's do an A times B. My result will be a 2 by 2. So hopefully we're getting faster at our multiplication. First row, first column ends up being just a -2 plus 0. And then I have a 7 plus a 6. Second row is going to end up being a 4 and 0. And then I have a -14 and a 10. All right, so this is A times B. I should have designated that. That's A times B. So now our question is B times A going to be exactly the same? Now, it's a little bit tricky to look at this and do it backwards, so I'm sort of a fan of rewriting, and I'm going to put B in front of A so I don't goof up my multiplication. And so I'm going to try to multiply these. So now I'm going to be taking this row times this column, and then this row times this column, putting B in the front so I do it in the right order. So B times A, let's see what we end up with. So I'm going to end up with a -2 and a -14. That's a -16. I already are questioning this because I was supposed to get a -2. If I do the next column, I end up with a -6 and a 35. All right. A -6 and a 35, that would be a 29. So I'm definitely thinking this is not going to work. So no, it's not the same. It is not commutative. It does matter the order that you are multiplying. So make sure when I give you a problem to multiply that you set the matrices up in the proper order to get that correct. All right, last problem here. It says, and this is an application, and it's such a great application of matrices. And this would be the kind of thing, now I hate to say I've dumbed it down, but I've sort of dumbed it down because this type of a scenario would take a lot more than just 3 little matrices that I've built. But I'm just trying to give you the idea of where this comes into play. And matrices can be used a lot within computer programs of, where you're just entering some sort of a number into a program. This is the background, what's going on within that program. So with computers being very, very relevant in our world today, and many of you might end up being a programmer of some sort, this is a good thing to learn how to do. So I'm going to give you a moment to read this first paragraph. Okay, so here's what we've got. Ultimately, you have this developer, he's building 100 houses. And so he kind of has his main houses. He's got 3 models that he's going to build, but each model can sort of be tweaked to either be a colonial look or a ranch look. All right, so that's really kind of like he has 6 different plans that he's building, 6 different houses. And if you add these all up, you'll see it adds up to 100 because he's going to build 100 houses. Now he's going to get really efficient with this. If he's going to build the same 6 houses, then what he wants to do is he wants to be ordering all of his materials kind of in bulk for these houses. So what we have here is that the concrete and the lumber and the brick that is needed for each colonial house versus each ranch house. So if he's getting concrete for a colonial house, he's going to need 10 units. But for the ranch, he needs 50. But he's doing a lot of colonial houses and he's doing a lot of ranch houses. So why not buy all the concrete together? And so over here, then we start talking about the money and what that costs. And so ultimately, what we want to do is we want to figure out what these 100 houses are going to cost. That's our goal. All right. So let's move on to the next slide. So yes, the question is, what's the total house cost to build all 100 houses? So first of all, he's going to do is he's going to figure out how much of each of the 4 kinds of material must be ordered. So we've got the 4 kinds of material, and we want to know how much he has to order. So you're going to multiply 2 of these matrices together. Do you know which 2 matrices to multiply? Well, it's all the houses and all the equipment needed. It's not talking about money yet, so we're not using matrix R. So we're going to multiply these 2 matrices. Now, do you know the order? Because that would be important. Do you want to do P times Q or Q times P? And really, you don't have options because it can only be multiplied one way. This is a 3 by 2. This is a 2 by 4. So you want to multiply it in the order it's set up, because you'll figure out for model A houses, this is how much concrete is needed. For model B houses, you'll see this is how much lumber is needed, and so forth. All right, let's get it set up. I'm going to take P times Q. Now P is a 3 by 2. Q is a 2 by 4. So my result is going to be a 3 by 4. That's a pretty big matrix. I left us room to do it right here. It's a 3 rows, 4 columns. All right, so to find this first slot, I'm going to take first row times first column. So that's going to be a 0 and a 1500. These numbers are going to get bigger, but I felt like I tried to make them, or I tried to the screenshot, but the numbers are easy enough. Maybe we could still do them in our head. Okay, next one is going to be this and this. So you've got 0 and 30. And then we're going to have 0 and 600. And then I'm going to have 0 and 60. Next row, 10 and 20 times each column. So I have a 100 and a 1000. That's 1100. Then I have a 20 and a 20. Then I have a 0 and a 400. 20 and 40. Now I'm going to take my third row times each column. So I have 1,000. Wait, nope, sorry. I'm going to have a 200 and a 1,000. So that's 1,200. Then I'm going to have a 40 and a 20. 0 and 400. And 40 and 40. All right, so I've got that matrix. Next part B, says, what is the cost of the materials for each type of house? Now you're going to start dealing with this cost matrix. And if you think about what we figured out, this number right here came from Model A concrete. This number is Model B concrete. This is Model C concrete. Okay, so this is all concrete. So ultimately, what I'm going to be doing, if you can imagine this is all the concrete. This is lumber, brick, shingles. Concrete, lumber, brick, shingles times concrete, lumber, brick, shingles. So I'm taking first row, first column, and this is, I think this is helpful to understand. I should have done this first, that these are the models. This is model A, B, and C. Whereas this is your concrete, lumber, brick, and shingles. I should have done that first, because then you can see you're going to be taking this 3 by 4 times this 4 by 1. So we're going to be taking our result. I don't know what to call that. I don't want to call it R for result. It's we're going to call it matrix N for new. Okay, we're going to take our new matrix times our cost matrix R. And you can see the 4s match up. So my result is going to be a pretty small matrix. It's a 3 by 1. And your 3 is going to be model A, model B, model C, and your 1 is going to be your cost. So here we go. We're going to take this row times this column, and at this point, we're going calculator. This is more than what I can do in my head. Maybe you can do it in your head. Go for it. I'm going to have to go ahead and go to my calculator. So you're taking each one of these numbers, each one of these, times each one of these, and adding it together. I'm going to go ahead and just pause the video. I'm going to find the numbers. I'm going to plug it in. All right, so I've got our numbers filled in there. So that's what all the Model A's for the whole development is going to cost in supplies. Really, all you're doing is supplies. There's no labor. And these are only part of the supplies, right? There's no plumbing involved here yet. This is just some of the basic stuff. So obviously, the house in general is going to cost more than this. But maybe this was just a particular order from a particular store, like Star Lumber or something. Okay, so, all right. And then we have to actually answer what the question is. What is the total cost to build all the houses? All right, so that just means you got to add up all of these numbers, which I already did for us. And so our final answer is 188,400 to buy these supplies for the 100 houses. All right. That's a good problem right there. I know there's a lot involved, but good to have that deeper level of thinking. So you're hopefully this helps. Get to your homework. Good luck.